Okay, so today we would like to talk about section 5.3. Section 5.3, least square problems, least square problem, and it's related to the material in section 5.1 and the section 5.2, but it also has some application for this, for the material in this section. It has some application, and actually in some field it's useful for the application. And to be honest, probably you also could see this result in calculus course. Yeah, probably you could see some relative result. Okay, so here we talk about section 3, least square problems. Square problems. Okay, so I erase E. Square problems. Okay, so let's recall. Okay, so in the beginning, when we talk about linear algebra, in the beginning we say that the goal is to solve the linear system. The goal is to solve the linear system. The linear system. And for the linear system, probably had some equation and some unknowns, and but it's linear. It's the linear system equals b1 equals b2 and so on. We have some linear system. We transfer it into, use the matrix equation and transfer it into this one. It becomes we want to solve this one. And A becomes, here is if we have n equation, and n unknowns, x1, xn unknowns, then it becomes the matrix A is n by n, and is our x, is our b, and x is n by 1, and b is n by 1. Okay, n is the n by 1. So originally solve the linear systems, and we transfer into this one, the matrix equation. And for this one, as we say, in the beginning we want to solve this kind of question. But here, solve this question means that you could see that if B belongs to, let's say, AX, here, if I give you a vector B, and this vector B belongs to this, say, AX, here X could be any vector, any n by 1 vector. Here X is exactly here. Actually, X we could rewrite it by this way, right? X1, x2 until xn. It's our vector X. Okay, so if we let X, if B belongs to, let's say, AX, X could be any scalar, any real number. X, I mean for each entry, x1, x2 until xn, if they be any real number, then let's say this one. Actually it's exactly the row, it's range of A. And it also means what? Because for this one, it's the material in section 3.6, I think. So it's A1, if you remember that, A2 until A, and so once we consider their range, it becomes x1 A1 plus x2 A2 until xn an. So that's what we say. Range of A is exactly the spanning set of their current space. So it's the spanning set. Actually, it's the spanning set. It's the current space of A. Current space of A. Okay. So if the vector B is given. So if I give you the vector B and B belongs to its range, or you could say current space of A, then of course we always could figure out the solution X, right? We always could figure out. But in this case, if B, then of course B equals, in this case, it exactly means this one. B equals A x1 xn for some and I belong to it's n by 1. And it also means that Ax equals b has a solution. This one is he has a solution. Right? If b belongs to its range, it means that Ax equals b. This equation has a solution. In other words, if b, let me see. Will you see? No. Okay. So if b doesn't belong to range of A, if b doesn't belong to the range of A, then X equals b has no solution. Okay. So I give you a matrix A and a vector B. If you want to know X equals b, this equation has solution or not, you could view it this way. If the vector b doesn't belong to range of A, then it has no solution. Yeah. But in this case, if it belongs to range of A, of course it must have solution. And in this case, even it doesn't have solution, our question is, can we find a, it's not exact solution, but it's a vector, and this vector has the nice result. This vector, once we consider b and ax hat, their subtraction, their length. This is a vector. Ax hat is also a vector. In here is n by 1, b is n by 1, here b is n by 1. So it's n by 1 vector, and it becomes n by 1 vector. So if for this n by 1 vector, their length, can we find a vector x hat such that its length, this one its length is minimum. So it means can we find x hat to minimize its length. And if we can, how if we can? And of course the solution is yes. And we use so the answer is yes. And we will use one example to tell you the result and to explain it. And I will give you one example. Yeah. Okay. Yeah. So now let me erase it. Our question is this one: can we find x hat to minimize the length of their subtraction? Yeah. B and the matrix A is given. B and the matrix A are given. So here I erase it. Okay, so now let's see. And I use the example to explain it. Here we have matrix A, 1, 1, 0, 0. Okay, yeah, and we have a vector B. 1, 1. 3, 1. Okay, so originally we want to solve x equals b. But actually for this question, if we want to solve it, if you remember that in chapter 1, what can we say? In chapter 1, we say that we consider AB, the augmented matrix. So it's 1, 0, 1, 0, 1, 0, 3, 1. So we multiply negative 1a to the second row, 1, 0, 3, 0, 0, negative 2. So multiply negative 1 here. You will get, yeah, it's fine. 1, 0, 0, so it's 3, 0, 0, 1, right? Okay, yeah, so here you will have 1, 0, you will have 0, 1 row. 0, 1 row, but it means that it's x1, 0 times x1 plus 0 times x2 equals 1. but it's contradiction. We don't have any solution S1, S2 satisfy this one, right? So it means that for this equation, it doesn't hold. It doesn't hold. It has no solution for this question. So in this section, we want to find a vector x hat such that once you consider the vector b and consider all the vector x, a and the vector x, their product ax, it means that all the vector in its range. Then once you consider their subtraction, it will be the minimum. It will be the minimum. If I could figure out the x hat, if I could figure out the x hat, it should be the minimum. It should be the x hat. It should be the vector such that its length is the minimum. Its length is the minimum. Okay, I should correct it. Okay, so here, yeah, so here, let's see. And here we could expand this part this way. As we say, we could expand it by its range. So what's the range of A? Range of A is exactly 1, 0, 1, 0, x1, x2 here, and x1, x2 is any real number. They are any real number. So it becomes s1 plus 0, s1 plus, so it's this one. S1 is any real number. So it's exactly Spain cell of 1, 1. Spain cell of 1, 1. Right? So its range is exactly Spain cell of 1, 1. But B, of course, B 3, 1 is doesn't belong to, so of course B doesn't belong to range of A. It's easy to see. 3, 1 doesn't belong to its Spain cell. It's Spain cell. Yeah. Okay. So now we want to explain it. So here you will see I don't have too much. So here, okay. So here I erase it and I explain it by the graph. Explain it by the graph. So range of A is a Spain cell of this vector. So this vector is this one. So range of A is this cell. Is Spain cell of A. So here, and what's the vector? 3, 1. 3, 1 is 1, 2, 3, 1, 2, 3, 3, 1, 3, 1. Yeah, x equals 3, y equals 1. 3, 1, 3, 1. This one. So here is our vector B. B is the vector 3, 1. 3, 1. So it seems there is some typo in the note, but you could correct it. Anyway, okay. So it's our vector B, and it's the range of A. So in the graph, you could see that we want to find a vector x hat, such that ax hat, if I call ax hat be the vector P, if I could denote it by P, then B subtract P, the length. What does it mean? The vector P must be the vector in its range. So probably it's this one, or this one, or this one, right? It must be a vector in its range. And we consider the subtraction, so it's this one. We consider the subtraction. For example, here we consider the subtraction. We consider the subtraction, or we consider the subtraction. Okay? And here, in the graph, you could see that so the length of the subtraction means the length, right? So of course, if it's minimum, then it means that it should be 90 degrees. In the graph, if we explain by the graph, you could see that, right? You could see that. So in this case, we denote it by P. In this case, we denote it by P. And the P is this one. P belongs to range of A, so we could figure out one vector x hat such that P equals ax hat. P equals ax hat. And here, for this vector, if I denote it by Q, so Q, then it's the x for another x, for example, x0, for another x0. Yeah. Okay, so, okay, for here I denote, I erase it. here, because here I will use this notation to explain it. Okay, so I mean range of A is 1, so we could see that there exists a vector P, there exists a vector P, P equals AX hat, this one, P equals AX hat. Oh, here I use this one. There is this vector P, P equals AX hat, this one, in range of A, such that P sub B subtract P its length. Here is the P subtract P, B subtract P its length is always less than B subtract Q. Yeah, I still use this one. B subtract P is always less than B subtract Q. Q. For all Q in its range. And Q is not equal to P. Q is not equal to P. For any Q in its range, it could be this one, or it could be this one, or it could be this vector, then its length is always greater than B subtract P its length. Right? In the graph we could explain it. So it means that B subtract AX, P is this vector, so it means that P subtract AX hat is just this case. It's B subtract AX hat is this vector. It's the vector B subtract P. B subtract P is this one. As we say, this vector is B subtract, let me see. Yeah, B subtract P. Here it's the B subtract P. The vector B subtract P is this one. Okay, so it's orthogonal to range of A. So it's orthogonal to range of A. So it's orthogonal to range of A. And in other words, B subtract AX hat is it belongs to range of A. It's also orthogonal complement. It's orthogonal complement. And here I erase it. So B subtract AX hat for this vector, it belongs to range of A is orthogonal complement. But range of A is orthogonal complement. In section 5.2, in the last week, yeah, it's the last result. As we say, range of A is orthogonal complement is exactly null space of A transpose. Null space of A transpose. Yeah, null space of A transpose. Yeah, so here we could see that this vector belongs to A transpose in null space. In other words, A transpose B subtract AX hat is equal to 0. Because it belongs to A transpose, this matrix is null space, so it means this one. So in other words, A transpose B subtract A transpose AX hat equals 0. So finally, you will see, we get this equation. We move this vector into right hand side, so you will get A transpose A X hat equals A transpose B. A transpose B. So you will get this equation. So what does it mean? It means that for this problem, I give you a matrix A. I give you a vector B. Originally want to solve X equals B, this linear system, or this equation. Yeah, but for this equation we don't have exact solution. But now we could find a vector X hat such that X hat, when we consider the difference between the vector B and all the vector in its range, it will be X hat, it will be the minimum. Compared with another vector, their difference, their length. B subtract this guy, their length, it will be the minimum. So if we want to solve it, we want to figure out the vector X hat, how to solve it. We could consider, for a matrix, we could consider A transpose A, and we can consider A transpose B. So now we could denote it by a matrix, for example, here we could denote by a new matrix. For example, we could denote by B, and the A transpose B we could denote by a new vector B prime. So now it becomes we want to solve B x hat equals B prime. Originally we want to solve it, now it becomes this one. And here B is the matrix A transpose A, and the B prime is the vector A transpose B. And for this equation, and of course for this equation, it must have the solution. And now, indeed, for this problem, we could solve it. So for this problem, our matrix B is, you consider its transpose. So its transpose is 1. First row becomes first column, second row becomes second column, and the A transpose A is exactly 2, 0, 0, 0. And the A transpose B is exactly the vector 1 times 3 plus 1 times 1, 0 plus 0. So it's 4, 0. It's 4, 0. It's this one. So we want to solve it. B, this guy. So we want to solve it. So we want to solve 2, 0, 0, x1, x2 equals 4, 0. We want to solve this question. It's our x hat. And for this question, what can we say? For this question, actually you could see that it's equal to 2x1. Since it's very easy to figure out, so we could do it directly. So it means that x1 equals 2. And x2, it could be any real number. We don't have any restriction. Right? So, So can we find x hat? Yes. So indeed, we could just let x1 be 2, x2 be any real number, then it's in the minimum. So the solution. The solution x hat is exactly the set. x1 is 2, x2 is any real number, so we could write it down in this way. Remember, I write down by x2, and s2 could be any real number. Then it's the solution. Okay, so it's the solution. If we want to minimize the minima, if we want to minimize B subject as AX hat, we want to minimize this guy. We want to minimize their length. Then we could use this way to solve it. And the way to figure out its minimum is called this square solution. So I write down the definition and tell you the general theory, and give you more examples. Okay. So here I write down the definition. Okay. So I write down the definition. The least square solution, of x equals b. Square solution of x equals b are the vectors x hat in Rn such that B subtract AX hat its length is minimum. Length is minimum. Length is minimum. So it's called, if the hat, the vector X hat is to let its length is minimal, then we call it, it's the question, it's the linear equation x equals b. It's this square solution. Yeah. So and our result, our theory. If you remember, for our example here we have a matrix A 1 1 0. How to and a vector B? We just consider A transpose, right? And we consider A transpose A, A transpose B, A transpose B. And originally we want to solve AX equals B, but now it becomes we solve A transpose AX hat equals A transpose B. So yeah, it becomes this question. So for our general result, for this equation AX equals B, we must have these square solutions, These square solutions X hat and it's the solution set of it's the solution set this one, right? This one. It's the solution set of A transpose A X hat equals A transpose B. Okay, so and in particular, if A transpose A, the matrix A transpose A is invertible, then X hat, let me see, could you see that? Then X hat is, yeah, X hat is exactly equal to, let me erase it, I write down here. X hat is exact. If it's invertible, we could multiply by its inverse in both sides. So it's exactly A transpose A, its inverse times A transpose B. This one, their product. Otherwise, you also could solve it by this way. We always use this way to figure out. Apply elementary law operation. Then left hand side is identity. Right hand side is what we want. S hat. This one. Okay, we always solve it by this way. Okay, so it's our general result. Yeah, so I will give you one more example. Yeah. Okay, let's see. So here I give you a remark and I give you one more example. So if we want to solve this kind of question, first of all we should compute A transpose A and A transpose the vector B firstly. And after that we solve A transpose A x hat equals A transpose B, this equation to get x hat, to get x hat. Okay. Yeah, this one. It's our remark. And now, yeah, and of course here you also could solve it by this way. Yeah, put it in this form, and the right hand side is what we want. Anyway, so let me consider more examples. For example, A is the matrix 1, 1, 1, 1, 2, 3. B is the vector 0, 3, 0. This one. And we want to find the least square solution. Least square solution of X equals B. We have a matrix A. We have vector B. We want to find the least square solution of X equals B. Okay, so yeah, find the least square solution to X equals B. Yeah, so here we could consider A transpose. So A transpose is for the first column, it becomes first row. Second column becomes second row. And we should consider A transpose A. A transpose is 2 by 3. A is 3 by 2. So A transpose A becomes 2 by 2. 2 by 2, and it's 1 times 1. First row, first column. So it becomes 1 times 1 plus 1 times 1 plus 1 times 1. And this entry is second row, first column. So it's 1 times 1 plus 2 times 1 plus 3 times 1. This one. And the next one is, this one is first row, second column. So it's 1 times 1 plus 1 times 2 plus 1 times 3. This one. This entry is second row, second column, so it's 1 times 1 plus 2 times 2 plus 3 times 3. This one. So it's exactly 3, 9, sorry, 3, 6, 6, 9. 3, 6, 6, and it's 14. 14. Yeah. This one. And A transpose B. A transpose B, the vector A transpose B. The vector A transpose B is exactly A transpose B is 1 times 0 plus 1 times 3, so it's plus 1 times 0. So just have we just need to consider this entry and this entry, since both of them are 0. So it's 1 times 3 is 3, and here is 2 times 3 is 6. So A transpose B is 1. So we should consider this one, this equation, and A transpose A is matrix, A transpose B is vector. But it also means we can consider this one. So now we consider this one, A transpose A. Here is our A transpose A and A transpose B. So A transpose A is 3, 6, 6, 14. A transpose B is 3, 6. This one. And here we multiply by 1/3, or otherwise we could cancel it firstly. So multiply -2e to second row, you will get 3, 6, 3. So it's 0, and 14 subtract 12, so it's 2. And 6 times subtract 6 is 0, this one. And 2 multiply -3a to the first row, so you will get 0, 2, 0, 3, 0, 3. This one. And here multiply by 1/3, multiply by 1/2. Finally, you will get it's equal to 1, 0, 1, 0, 1, 0. This one. So what's the solution? The solution is this one. The solution is exactly this vector 1, 0. This vector. I mean, so the least square solution, the least square solution of Ax equals b, or to X equals b. This square solution to Ax equals b. Our matrix A is this one. Our vector B is this one. Is the vector 1, 0. The vector 1, 0. Let me see. You see that it's our x hat. It's our x hat. Here is identity, and here is our y1. Okay. Yeah. Okay, so for this one, see it's not typical one. Just we should practice some. But for this question, actually, what's the original linear system? Here we just say the matrix A is this one, the vector V is this one, but it has the corresponding original linear system. I mean, probably original our problem is this one. x1 plus x2 equals 0. x1 plus x2 equals 3. x1 plus 3x3 equals 0, right? It's this one. So we consider it's augmenting matrix 1, 1, 1, 1, 2, 3. This one. And actually you also could do it, and once we let x be x1, x2, once you consider x is exactly, yeah, you can see x is exactly x1 plus x2, and x1 plus 2x2, x1 plus 3x3, so exactly our vector b, yeah, this one. I mean, probably original linear system is this one, and it means the same thing. Okay, so now I give you one more example and use this form. I mean, originally we have a linear system, s1 equals 1, s1 plus s2 equals 4. Ooh. Sorry. I should be careful. Okay, so the first one is x1 equals 1. s1 plus s2 equals 4. s1 plus, let me see, yeah, s2 equals 5. This one. Oh, by the way, here in this statement, you could see that once you see the original linear system is this one, so right? So here you could see for these two equations, you could see that x2, just use the second equation, subtract first equation, you will see s2 equals 3. s2 equals 3, then plug in the first equation, you will get s1 equals -3. So -3 plus 3 is 0, -3 plus 6 equals 3 is fine, but -3 plus 3 times 3 is non-zero. So indeed, for this linear system, we don't have solution. Right? So we just could figure out this square solution to x equals b, and it's exactly the vector 1, 0. And now we consider another example, and it's our example. And in this example, you also could see that s1 equals 1, plug into second equation, you will get s2 equals 3. But once we plug into the third equation, you will get s2 equals 4. So it's a contradiction. So indeed, for this linear system, we don't have any solution, but we still could figure out this square solution to x equals b. We still could figure out this square solution to x equals b. Okay, so for this one, we consider its corresponding, its augmenting matrix. So it means it's equal to, could be this way, it's plus 0 times S2. So could be this way, it's our matrix A. Matrix A just the augmenting matrix. So S1 is 1, 1, 1, S2 is 0, 2, 2. Sorry, 0, 1, 1. And I should say, sorry, I should correct. Here, this part is called coefficient matrix. Coefficient matrix. And the B is this one. 1, 4, 5. 1, 4, 5. This one. Let me see, there is something wrong. 1, 2, 4. 1. Yeah, probably there is something wrong for the original question. There is some typos I fix it. I mean, it should be 2, 4. So for the question, it should be S1 plus 2S2, S1 plus 4S2. And it's equal to 1, 4, 5. That's correct. Sorry, I should fix it. I should correct it. So indeed, now it's 1, 0, 2, 4. It's correct. It's correct. And even in this, even we solve it directly, I think it's also contradiction. I mean, here you could see plug it into second equation, you will get it's equal to 3 over 2, right? And plug it into third equation, you will get S2 equals S2. Yeah, here is 2x2 equals subtract 1, so it's 3. And here subtract 1, so it becomes 4. 4. But it's contradiction. It's contradiction. It's contradiction. Okay, so now we just could figure out the least square solution to x equals b. And how to solve it is the same. We use the same process. The same process. So first of all, its transpose is first column becomes first row, second column becomes second row, and we should consider A transpose A. A transpose A is first row, first column, so it becomes 1 plus 1 plus 1. And first row, second column, so it's 1 times 0 plus 1 times 2 plus 1 times 4. And the second row, first column is 0 times 1 plus 2 times 1 plus 4 times 1. 4 times 1. And 0 times 0 plus 2 times 2 plus 4 times 4 is this one. And so it's 3, 6, 6, 20. And the vector A transpose B is exactly 1 times 1 plus 1 times 4 plus 1 times 5. And the 0 times 1 plus 2 times 4 plus 4 times 5, so it's 20. So it's 10, 28. Let me see A is something. Oh, sorry. What happened? It's different problem. Okay. Anyway, so I think I follow the one in my notes. So in my note, I just write down 1, 3, 4. So here we fix it again. Sorry. 1, 3, 4. 1, 3, 4. But it's the same. Here, if it's 1, 3, 4, it becomes 3 subtract 1 is 2. 4 subtract 4. 1, 3, 4. So 4 subtract 1 is 3. So indeed, it's a contradiction. And here, so here it becomes 1 times 1 plus 1 times 3 plus 1 times 4. And 0 times 1 plus 2 times 3 plus 4 times 4, 16. So finally it's A, 22. A, 22. This one. Yeah. Okay. And so now we want to solve So now we want to solve A transpose A x hat equals A transpose B. This linear equation. We want to solve this linear equation. So just consider 3, 6, 6, 20, and A22. A22. This one. And now again, apply elementary law going to solve it. To figure out its reduced rational form. So multiply negative 2a to the second row, so it's 3, 6, 8. So it's 6 subtract 6 is 0. So as you see, we often use this way to solve it. So 20 subtract 12, so it's 8. So 22 subtract 16, so it's 6. It's 6. Yeah. And here we multiply by 1/8. So you will get it's 3, 6, 8. So it's 0, 1, 6/8. 6/8 means 3/4. 3/4. And multiply negative 6 and a to the fourth row. A to the fourth row. So it's 0, 1, 3/4. And it's 3, 0. And here, what's this? It's 8. Subtract 3/4 times 6. So now we cancel 2, so it becomes this 1. And 8 is equal to 16/2. Subtract 3 times 3 is 9/2. So it's 16 subtract 9. So it's 7/2. 7/2. This one. But it's not really identity, so we should multiply by 1/3. So finally, let me see if you see that. No, it will be better to write down here. So it's 1, 0. So divide by 3. So it means multiply by 1/3. So it becomes 7/6. And it's 0, 1. And it's 3/4. 3/4. So it's this one. And this one is exactly our x hat. It's exactly our x hat. Yeah. So it's exactly this. Let me see. Yeah. This square solution to ax equals b. Ax equals b. Now this square solution to x equals b is exactly this one. Exactly this one. For this question. Okay, that's the first part about this section.